Examples. Number 1. The distribution of heights of women aged 18 to 24 is approximately normal, with a mean of 65 inches and a standard deviation of 2.5 inches. Half of the women have a height of at least how much? Well, since we're told that the distribution is normal, you want to think of that bell-shaped curve that we talked about earlier. And for the bell-shaped curve, the mean occurs right in the middle of that bell. So therefore, half of the women have a height of at least the mean. So our answer here would be 65 inches. Part B, what are the heights of the middle 95% of the women? Well, the middle 95% fall within 2 standard deviations. So if we have x bar minus 2 standard deviations here, and then x bar plus 2 standard deviations, we will have 95% of the data appearing between these values. So we need to figure out what those quantities are equal to. So the problem tells us that our standard deviation is 2.5. So we're going to do 2 times 2.5, which will give us 5. So now we take our mean and we subtract 2 standard deviations, which gives us 60. And then we take our mean and we add our 2 standard deviations, which gives us 70. So 95% of the women are between 60 inches and 70 inches. Okay, for part C, the tallest 2.5% of women have what minimum height? Okay, well, if you remember from the last page, well, actually, we can refer to the last problem. Since we know that the middle 95% are within 2 standard deviations, okay, that means that we have 5% of the data not accounted for. 5% is, or 2.5% will be smaller than 2 standard deviations from the mean, and the upper 2.5% is going to be more than 2 standard deviations above the mean. So the way I got 2.5 is I know on either side, when I add those to my 95%, it should give me 100%. So there's 2.5 in that upper right-hand side. So the tallest 2.5% of women are going to have a height of at least 70 inches. So that's going to be the mean plus 2 standard deviations, which is equal to, let's see, our mean was 65 plus our 2 times 2.5, which gave us 70 inches. Okay, going on to number 2. The box plot of birth weight in ounces of a sample of 160 infants born in a local hospital is shown to the right. The median birth weight is approximately, well, with a box plot, we know that the median is going to be the line that's drawn in the middle, our second quartile. So that looks like it's approximately 110. Approximately 25% of the infants weighed below what birth weight? Well, 25% would be lower than the first quartile. And we see that the first quartile looks like it's approximately somewhere around 105. Okay, so I see 104 is one of my choices, so that would be our answer. Okay, the number of children with birth weights between 100 ounces and 120 ounces is approximately. Okay, well, if we look at our box plot, that range is approximately from Q1, the first quartile, to the third quartile, which is the upper part of the box. And this is where the middle 50% of the data lie. So how many birth weights did we have in our sample? We actually had 160 infants. So what we want to do is take 50% of 160, because again, we know 50% of the data points will lie between the first and the third quartile, and that gives us 80. So that would be our answer. And again, this is approximately. Number 3, in a statistics class with 136 students, the professor records how much money each student has in his or her possession during the first class of the semester. The histogram to the right shows the data collected. Okay, so we see that more than 60 students had between $0 and $10. Then somewhere around 45 students had between $10 and $20, and so on. How can you describe the shape of the graph? Okay, well, this graph has a tail that seems to be going to the right. So this graph would be skewed right. Part B. What can you conclude about the relationship between the mean and the median? Okay, well, since we have a few very large values, that's going to make the mean larger than the median. Remember, the median is in the middle of the data. So since most of the data occur in the smaller, towards the left of the graph, the median is going to be over here, whereas the mean is going to be somewhere larger. So for something that's skewed right, the mean is going to be larger than the median. Part C, a possible value of the median is, well, how many students were we talking about? 136 students. So what I'm going to do is take 136 divided by 2, which is 68. So the median is going to be somewhere around the 68th student. So if you look at the first bar, we have a little over 60 students that had between $0 and $10 in their pocket. And then we jump down to between $10 and $20. So the median is actually going to occur somewhere within that response. So a possible value of the median has to be something between $10 and $20. So 12 would be our answer. Okay, in our last example, a reporter wishes to portray baseball players as overpaid. Which measure of center should he report as the average salary of major league players? Okay, keeping in mind the reporter wants to show them as being overpaid. Should he use the mean or the median? Well, not the median, because the median is going to give you the value that's right in the middle. If the reporter wants to inflate it, remember, all you need are a few people with a really high salary, and once you find the mean, it's going to be a larger number that isn't necessarily representative of the sample. So the mean would be the best way to inflate it. Okay, so if you read through C and D, neither of those are relevant. A would be our answer.